I will present you the work we are currently doing with my colleagues Marion Charlier from Stelligent and Marc Brasseur also from R&D here in ArcelorMittal concerning the modeling of cellular beams in SAFIR and the tools we are currently developing to automatize this modeling in GmSAFIR specifically. So here you see quickly the content of the presentation. I will first go through a presentation quickly of cellular beams, what it is and why we want to model them in SAFIR. Then I will show you the tool that we are currently developing, how it creates this geo file and how it's implemented then in GmSAFIR. We used to do this a lot with JIT before, so the tool was validated and working very well. So now our idea was to just adapt it, so just to adapt the language to GmSAFIR. Is not as easy as we initially thought, so it's still ongoing. I thought it would be finished for this presentation, but in fact still under development, but is also nice to share, I think, the development. And we implemented then a cellular beam, and we will compare the results we get with SAFIR with a real scale test and also with analytical methods to show how SAFIR behaves in these cases. So first of all, cellular beams are those beams with large web opening, circular most of the time and regularly spaced. It's quite used and quite useful to achieve large span. It has high inertia for the light, a reduced amount of steel, but of course it comes with additional failure modes. So two main ones are web post buckling. So the web post is this part you have of the web in between two openings. And you have also Virendel. I will not go too much into detail, but it's the global opening failure that occurs because of the shear flow around the opening. As I said, those beams, they have high strong axis inertia, but quite weak inertia in the weak axis. That's why they are quite prone also to lateral torsional buckling. I will directly jump to the tool. So here is the interface. As I told you, it's still under development. This is just now for internal use. So I will quickly show you how it works. You have here all of the geometrical data that you have to enter for the cellular beam. So opening, spacing, length of the beam, and thickness of the plates. Here you have imperfection for lateral torsional buckling. And here, so this is the global imperfection. And here is more local imperfection for web post buckling. I show you here how it looks. So you could implement a global imperfection on the beam to target lateral torsional buckling and assign wave in the web for the web post buckling. Those shapes, they come from the Egon-Mond analysis, especially for the web post buckling, which is the first mode. You can, of course, implement all of the material data for the G4S. This is not yet implemented. I will go to it a bit later. So if I just click on this button now, this window pops up and it tells me that it created the geo file. I just have to open GmSH and open it, and the cellular beam will be automatically drawn. So I quickly show you. I have it here. It's just created. If it opens. Okay. So here we see it from the top. You see the wave from the lateral torsional buckling imperfection. And if I rotate, I see all the openings. So this is directly the translation from JIT. And with JIT, we used to directly mesh and create the in file. But here, this is where we experienced a bit more trouble with GmSH to mesh, because now if I go through only the basic mesh as is described in the first videos of Jean-Marc in YouTube, I would click on 2D. It would automatically by default make this triangle element that we do not see here, but I press recombine to have a square element, because in my knowledge, this shell element, they only run in SAFIR with a rectangle element. And then I would refine by splitting to have a more proper mesh. And here, as I see, I have warnings, but no error, but I can directly see that my mesh is quite strange. As I said, we are using GmSH now, not for a long time, and I don't know if there is a way to just like this to prevent this problem, but we anyway find another solution, which takes a bit more time. Searching a bit and playing, if I go on the mesh option, I can change in the general and select, instead of this frontal Delaunay, which is by default, I select this quasi-structure quads, which is experimental. I guess it's because it's not yet fully validated. But now if I press again the 2D mesh, I would get, if it works, directly squared element. And by directly refining, by splitting, I get the mesh which looks more clean and works a bit better, but still we do not like so much those slender elements, slender parts in the top T here. Even if I refine, I get quite unstable, not unstable, but quite irregular shapes. So to avoid this problem, we decided to go through the transfinite option. So let me come back to the presentation. So this I showed you. Yes, here, summary of what I said. We had problem using the recombine. It was still some triangle element, and the mesh is not matching perfectly the geometry. And we could not have a satisfying mesh, I would say. To use this transfinite function, you have to have the shell element with only 4 edges, and then you can transfinite the lines and the surface. So this is how we had to discretize our geometry. So we simply cut the beam in several elements with only 4 edges all the time. And then you have to transfinite all of them, which takes time and which makes, in my opinion, a lot of sense to have an automatic tool to do it automatically and not to have it to do it one by one. But this is what we have done yet, because this was the first test. It was the first time for us we modeled a cellular beam with GmSH. So we had to select every small surface like this and enter here the number of elements. To have a structured and a regular mesh, it's better to put the same number of points on edges facing each other. So here, for example, is 10, 10 and 7, 7. And here you have to do the same in a second step for the surface. So we transfinite the surface and we select the boundary points. Doing this on the whole beam, you get this kind of mesh, which is much more regular and much more easy to use, especially if you want to extract the local forces and you want to see what is happening in the top chord and in the bottom chord of the cellular beam. And it's quite also nice to parameterize. Let me show you another quick demo on how it works with the geo file. If I now open this this file, the new file that we created. Okay, I will open the geo file and just make the mesh. So here, as everything is already transfinated and implemented, I just press 2D, and normally I have the mesh, which is done, which is quite rough for this one. But then if I want to improve the quality, I don't need to play with the geometry in the interface. I just go to edit the script. In the geo file, I look for the transfinite, and we grouped the transfinite in the text in the geo file into 3 groups. So we have 3 transfinite curve, as you see here, here, and here, and I just have to change the number of points of each of them if I want a more refined match. So I will do it quickly. Here I have a group of elements of 4 points per line. I would put 8. Here I have 7. I would put 12. And on the last one, where I have 2, I would put 4. And I just close the window. And now if I reload the script and I just mesh, I would have a much more refined mesh quite fast, I would say. Let me go back. So next step now, we did not yet, as we understood, implemented this in the tool. So this would be implemented, and then we will automatize also the creation of the G4S to have all of the properties to run more efficiently those simulation. So now we come to the last part, analysis of results. So we modeled this test that was performed in the 2000s by CTICM. So it's a 4-point bending test on a cellular beam. The target was web post buckling, so the failure target. That's why you see that it was maintained laterally. So we have no lateral torsional buckling, and the web posts are quite narrow to really target the failure in this area. This test was performed at ambient temperature. So for now, we will just focus at ambient temperature. Here you see how it looks in diamond. The material properties were measured in the test, and we implemented, of course, the steel grade, proper steel grade in SAFIR also, and we used steel EC3 2D as the material. For the imperfection, we put only one in the web for the web post buckling, and we took this time the value that is advised by the new version of Eurocode 3.1.14, and it would give an amplitude for the sine curve of 1.77 millimeter, which is higher than the one that was measured, but we wanted also to have a look on what is the influence on this in this case of Eurocode and how the overestimation would be safe-sided. Here you have the first result. So you see on this curve the deflection compared to the force. The curve with the triangle is the test, and the curve with the dots is SAFIR. You see that we put a quite heavy model. It has almost 14,000 nodes, but still it took less than 5 minutes to run. So in my opinion is reasonable. The stiffness is really well captured. However, a bit safe-sided in terms of failure load. We have 305 kilonewton for the test and 275 kilonewton for the numerical simulation. It's 10% different. This is mainly due to the imperfection. I don't have, unfortunately, the results with the correct imperfection in SAFIR, but 10% with a higher imperfection looks really reasonable. We did a bit of other simulation and to study the influence of the mesh size. So here is a much smaller amount of nodes, 1,800. It runs faster, but you see that in terms of stiffness, we start to have some doubts. But failure load is the same. Here you see the mesh sensitivity analysis that we've done. So the first graph in the middle is the influence of the mesh size in the horizontal axis on the deflection at mid force, I would say. So 150 kilonewton, and you see that for the mesh size around 3 centimeters starts to be quite consistent, but we overestimate the stiffness for higher size of the mesh. And for your information, this picture that I put is around 5 centimeters, the size of the mesh. So we overestimate a bit, is the triangle in the middle here. This is exactly what we see here in the curve. However, for the failure loads, it starts to be consistent, starting from the mesh size of 10 centimeters, which is much bigger, and then it's really consistent with the smaller sizes. With bigger ones, we had problem of convergence, and it stopped really early. Just a comparison with GID. So here you see our previous model with GID. So here the mesh is not as structured, but this is the default parameter we had in GID. So we didn't need to cut the beam in several shell elements. It was just the full web. That's why you see it's much less organized. And with now 9,000 nodes, we get exactly the same results as with the GmSAFIR. So you see the crosses compare to the dots for GID and GMSH. It fits perfectly. Comparison of the shape. Again, the buckling shape looks quite accurate without increasing the displacement scale. And here you see we increased a bit the scale to see which web post is critical. And it fits perfectly with the results that were obtained in the test. Now we performed a quick comparison at elevated temperature, but this is purely analytical. So here you see the results of the critical temperature calculation performed with the new version of Eurocode, which is Eurocode 3113 for the ambient temperature calculation. It's the main core of the standard for beams with web openings. And you have an Annex E in Eurocode 312 that deals also with these web openings at elevated temperature. So this calculation is performed with our software ACB+. And you can see on the last column of the tables the critical temperature of the beam that we modeled in ACB+. So the first table here is related to the failure of the opening. So it's Virendel effect, basically. Then you have the web post checking, shear force here, and buckling. And then you have the gross cross-section checking. So the critical temperature is the lowest for the global failure of the beam, and we get, with the analytical method of Eurocode, 508 degrees. Comparing with SAFIR, so we modeled as a frontier constraint and SAFIR on the shell elements, we get a failure after 847 seconds. If we open the TSH of the web at this time, so we had time step around 832 and 864 seconds, it gives a temperature between 500, around, I would say, 510 degrees, which matches perfectly with the one calculated analytically, which is quite also a positive conclusion. This was my last slide. Thank you very much. And as I said, still under development. Hopefully, it will be the tool will be usable soon, and maybe we'll share if of course if any need is required from any side. Thank you very much.